This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome to Chapter 3 of Space Oddities, Uncommon Discoveries in the Cosmos. In this episode titled Alien Worlds, Strangest Exoplanets Discovered, we're about to embark on a journey to explore some of the most bizarre and fascinating planets beyond our solar system. Get ready to uncover their unique characteristics and what makes them truly out of this world. Let's dive in! A world where it literally rains molten glass. Another where metals turn to vapor and race through the sky at supersonic speeds. And somewhere in the dark between stars, a planet drifts alone, with no sunrise, no sunset, just endless, frozen night. Astronomers used to think our solar system was a decent template for how planets should look. Then the exoplanet census exploded. With more than 5,300 confirmed worlds on the books, the rule now is, if it doesn't break a pattern, it's probably just not weird enough yet. We've found planets skimming so close to their stars that a year is shorter than your weekend. Others swollen into puffy gas balloons barely denser than styrofoam, and compact worlds packed tighter than a city of skyscrapers built from lead. Some orbits are tilted wildly, as if the planets were flung into place by a cosmic brawl. Others run backwards, orbiting opposite their star's spin. As new telescopes stare harder, we're not just counting worlds, we're starting to read their climates, seasons, and storms from flickers of starlight hundreds of light-years away. Out beyond those first headline-grabbing oddballs, the catalog keeps getting stranger. Some worlds hug their stars so tightly their surfaces glow like forge-hot metal. Others are swollen and airy, with the density of compacted smoke. A few may be loaded with carbon, turning the idea of rocky planet into something more like a gemstone mine on a planetary scale. And then there are the drifters, objects the size of Earth or Jupiter, cut loose from any system and wandering the galaxy. Each new find is a data point that stresses our theories, the way a stress test pushes a bridge design to failure to reveal its hidden flaws. If you zoom in on a few of the most extreme worlds we've found, each one breaks a different rule we thought we understood. Take 55 Cancri E. It's only a bit bigger than Earth, but far more compact, hinting at a carbon-heavy interior squeezed to brutal pressures. In labs, carbon crushed that hard can turn into diamond. On this world, the same physics might operate on a global scale. Instead of continents and oceans, models suggest an interior layered with exotic carbon phases and a surface that may be more like a volcanic foundry than a familiar rocky crust. Its dayside glows at thousands of degrees, so any solid ground is in a constant battle against being melted, eroded, or resurfaced. Then there's WASP-12b, a classic hot Jupiter taken to the extreme. It orbits so close to its star that it's being distorted into an egg shape, stretched by tidal forces. Gas is literally being pulled off its atmosphere, forming a stream that spirals toward the star like smoke into a furnace vent. Observations show the planet's orbit slowly shrinking, evidence that it's spiraling inward to a fiery end on astronomical, but not unimaginable, timescales. HD 189733b, meanwhile, taught astronomers that color can be deceiving. Its vivid blue hue, once loosely associated with oceans, turns out to be the signature of tiny silicate grains in its upper atmosphere, scattering blue light. When high winds loft these particles, they can seed colossal storms. Instead of gentle weather cycles, we're looking at a world where cloud physics runs on minerals, not water. And not every strange world even has a star. OwlUp 2016 BLG 1928 flashed into existence for us during a brief microlensing event, its gravity bending a background star's light for less than an hour. It appears to be roughly Earth mass, drifting on its own. Without a host star's glare, such objects are almost invisible, hinting that there could be more of these loners than there are stars in the galaxy. Together, these outliers force theorists to rebuild formation models that once treated star systems as orderly, closed families. Now, scattering, migration, and outright ejection are part of the standard script. Think about how we even know these bizarre worlds are out there. Astronomers watch for the tiniest dips in a star's brightness or for a subtle wobble in its motion, then stack thousands of measurements until a pattern emerges. It's less like snapping a photograph and more like reconstructing a city's skyline from the shadows it casts at different times of day. One carefully timed dimming reveals a world's size. Repeated wobbles hint at its mass. Combine the two, and you get density, which in turn whispers clues about what the interior is made of. Add spectra, light split into its colors, and you start teasing out atmospheric ingredients, pressure, even hints of global circulation. Here's where that one analogy helps. Studying these extreme worlds is like testing recipes at the very edge of what an oven can handle. Push the temperatures, swap ingredients, and you learn which physical rules always hold and which were just habits shaped by our single local example. These extremes hint that normal may be rare. As surveys widen, we might find that tidy, stable systems like ours are the outliers, not the rule. JWST and its successors will push from flashy giants toward quieter, Earth-sized targets, letting us test whether rocky worlds commonly keep air, water, and chemistry long enough for life. Your challenge this week? Pick one weird world and follow new papers or mission updates about it, like tracking a favorite underdog team season. Each new outlier we log quietly upgrades the software we use to think about reality. Laws of physics stay the same, but their outcomes turn out to be wildly flexible, like one codebase spawning bizarrely different apps. As surveys grow sharper, don't be surprised if our own world starts to look like the unlikely edge case in a much stranger catalog. Try this experiment. Tonight, recreate an exoplanet weather report for 3 real worlds mentioned in the episode: WASP-12b, HD 189733b, and TRAPPIST-1e, using whatever you have at home. For WASP-12b's scorching side, aim a desk lamp or flashlight at one side of a dark-colored ball to feel how intensely one hemisphere warms. For HD 189733b's glassy winds, sprinkle a pinch of sand or glitter in front of a fan to visualize sideways shards blowing past. For TRAPPIST-1e, put an ice cube under a lamp and touch it every few minutes to imagine a temperate zone between frozen dark and hot light. As you do each mini-demo, say out loud what the forecast would be if you were standing on the surface there: temperature, sky color, wind, and how long your day might feel. Notice which world feels weirdly most livable to you, and jot that one down to look up new research on later this week. This was OwlUp, your daily step forward. This series continues with more chapters on OwlUp.co. Visit OwlUp.co to access the complete course and continue your learning journey. See you there!